Hey folks, you have finally made it onto topic 1.8, equipotential surfaces. By the end of this video, you will be able to draw field lines. Ooh, yikes. Let's go ahead with the highlighter instead of that pen, right? You'll be able to draw field lines and equipotential surfaces for different electrostatic setups. So let's go ahead and start by talking about what exactly an equipotential surface is. So an equipotential surface is any area where the electric potential is constant. So what that means is if you were to move from one point on an equipotential surface to another point on the equipotential surface, you would not have to do any work to make that change in position happen. So let's go ahead and talk about the relationship between equipotential surfaces and field lines. And what I'm going to do is I'm going to use this this thing that you're used to, which is the field lines between a set of parallel plates. So as you may or may not remember from our parallel plates video, the potential between parallel plates depends on how far away from the top plate you are. So we have, if we have 12 volts of potential at the top plate, 0 volts of potential at the bottom plate, we will have half that potential halfway between the plates. And so at each point in space, I have the same potential if I move horizontally. So it does not take work to move parallel to one of my plates. So if I go from here, from point A to point B, I do no work. So these lines here are equipotential surfaces. And actually, what is really cool about equipotential surfaces is they will always be perpendicular to field lines. So if you aren't sure how to draw your equipotential surfaces, find your field lines, get a protractor, draw a 90-degree angle, and there you have it. So let's talk about the equipotential surfaces for a point charge. So here is my positive charge. I'm going to go ahead and draw my field lines. So remember, my field lines go out radially from my positive charge. I'm going to go ahead and see if I can draw these guys nice and neat. And let's go ahead and draw our equipotential surfaces. So let's start with this field line. Here is 90 degrees to my field line, and I'm going to go ahead and do that for all of my field lines. 1, 2, 3, 4. And so on and so forth. I'm going to go ahead and just draw around here all of my lines. So what you'll actually find is that your equipotential surfaces for a point charge are concentric circles around that point charge. And I'm trying to draw these nice straight lines. I'm semi-succeeding. So for your point charge, if you're trying to figure out your equipotential surfaces, you're just going to draw nice concentric circles around the charge. So let's talk about our equipotential surfaces for two like charges. And again, I'm going to start by drawing my field lines. So remember, my field lines are going to kind of go, let's start this way. They're going to go out of my positive surface on both sides. And they're going to kind of arch away from each other because our positive charges are repelled by one another. And so it'll be the same for my second charge. And when I draw my equipotential surfaces, what I'm going to get is this kind of like peanutty shape. So we're going to start going around like this. And then things are going to dip in here. And we'll continue around our second charge. And this divot here will get less and less distinct the farther away from our charges we get. So it's going to be kind of more like that in my second set of lines. So when you see two like charges, think two peas in a pod, it's peanut shaped. What about two opposite charges? Well, we know that our line is going to flow out of our positive charge and into our negative charge, into our negative charge and out of our positive charge. And that is going to be the same at all points on our field. So here's our field line here and here. Go ahead, keep drawing those field lines. And I can now draw my equipotential surfaces. And what's kind of cool about these is they look somewhat similar to our equipotential surfaces for two like charges, except the field between our two charges is a bit stronger than farther away from our charges. So what we'll get is this kind of almost Doppler effect going on. So we'll have a circle like this, and a circle like this. I can't quite fit. And it'll be the same around our negative charge. So we're going to have those nice circular shapes. But as you can see, the spacing here is going to be slightly less than the spacing here. So we'll have circles like with a single point charge, but shifted so that the center of the circle is slightly farther away from the is slightly farther away from the center of our two charges than the charges themselves are. So the centers will be farther apart than the charges are. Okay, so last one, let's talk about a conducting sphere. So remember that outside of a hollow conducting sphere, the field lines are the same as they are for a point charge. So let's draw those. Recall as well, we have no electric field inside the sphere, so I have not drawn any field lines inside the sphere. The equipotential surfaces from a conducting sphere are going to be the same as they are for my point charge, except for, again, I'm not going to worry about equipotential surfaces inside the sphere since I have no electric field inside the sphere. So pretend these are perfect circles. We have concentric circles around the conducting sphere. And that is that. So let's talk takeaways. First of all, you learned that no work is required to move a charge between 2 points on an equipotential surface. You also learned that equipotentials are perpendicular to field lines and they are parallel to each other. So if they're perpendicular, if two lines are perpendicular to the same line, you know that they have to be parallel to one another. And so that means that equipotentials will not cross over each other. And then finally, we did not talk about this earlier, but one thing that's important for you to know is that equipotentials are scalar quantities. So they do not have directions. And you can remember that because the potential, the regular potential, is also a scalar quantity. So potentials are scalar, and therefore equipotentials are scalar. So there you have it, folks. You now know what an equipotential surface is, why it's useful, and how to draw your equipotential surface for a few different electrostatic setups.